All right, so Mr. Ed Woolery, would you like to tell me about how you got to UK?
Sort of a long and winding story of sorts. I came originally to UK as a master's student. Well, let me back up before that, so it's even a little bit more. So after graduating with a geology degree in 1985, I went to work for the Department of Defense for a while, and worked a little bit with some mapping programs with the DoD, and then became tired of some of the security issues surrounding that job. So I moved over to the Army Corps of Engineers as a civilian employee there, and at that point, it's the Corps of Engineers and not the Corps of Geologists, and so I was noticing that there was sort of a disconnect between what the engineering folks were doing and what the geology section was providing them. And so I decided to go back to school and become an engineer. And so I came back to UK originally as a civil engineer, and in doing that, I as a geologist who was, I guess, rather proficient in math. My engineering professor introduced me to geophysics professor in the geology department. So the next thing I know, in addition to doing the engineering degree, I'm doing a master's degree, and and so I thought that was.
Yeah, well, so basically you were a geologist, and then you were an engineer,
right,
and then mix them together.
That's exactly right, and so I ended up with a master's degree in geophysics.
Right.
Which is essentially a mix between the two, and then I thought that would be it. But the next thing you know, I'm working on a PhD, and so I finished the PhD, went back to the Corps of Engineers, and working as a both an engineer and a geologist, geophysicist at this point, and was happy with what was going on, and then the Kentucky Geological Survey, which is here on campus, decided that they were going to initiate a geologic hazards program, and so which geologic hazards is really a
like
mix.
Earthquakes,
landslides, karst, if you recall, the Corvette Museum,
sinkholes,
the sinkhole development.
Yeah.
So all of these things are geologic hazards, and so it's really a mix between geology and engineering. And so they recruited me back to start the geologic hazards section, and that was probably 1999. And so I worked here for a couple of years, and then the next thing I know, the Department of Geological Sciences at the time recruited me over as from here over to the department as a faculty member. And so beginning in 2001, I started as an assistant professor in the geological sciences, and so I still retain a faculty associate position here at the Kentucky Geological Survey. Again, we run the seismic network for the state. I help the geologic hazards folks downstairs with that effort.
So you teach classes?
Yes.
As well as go out in the fields and do all these experiments with the Geological Survey.
Right. So I guess I'm just a regular faculty member. Teach classes,
Cool.
advise students,
Yeah.
and then work with the elements here in the geological survey, the geologic hazards. I've worked with the mapping section, the water section, and the energy section. So I've worked with most of the elements here at the survey. So I do a lot of Kentucky-based research, and most of it is focused on the seismic hazards out primarily in the New Madrid seismic zone and the Wabash Valley seismic zone in western Kentucky, the Mississippi embayment, and then of course the Wabash Valley of southern Illinois and Indiana. So that's where the majority of my research is focused. Recently, I've become more active with some other professors in the department, working in the eastern high Sierra of California and the Teton Range of Wyoming.
That's cool.
But everything's all field-based.
So you go out there?
Yes, go out and we do field-oriented experiments, and so I'm really an experimentalist and not so much of a theorist who
you don't want to just sit around. You want to get out there.
Get out and enjoy the outdoors, and these are great laboratories. These are
that's great.
Yeah, some of the best, the Tetons and the Sierra, some of the most phenomenal laboratories on Earth as far as that goes for intraplate seismicity or earthquakes that occur within on the inside of a tectonic plate. The New Madrid seismic zone is a world-class area to study.
Is there really a threat of earthquakes in these areas?
Yes. So in between December of 1811 and February of 1812, just out on our western border here in Kentucky, we experienced at least 3 large earthquakes.
Wow.
A sequence of them, probably mid 7 magnitude, mid 7 range, and so something like that, if an event like that were to happen today, then there'd be a lot of damage.
Yeah, you'd want to know about it.
That's right. During in 1811 and 1812, that was still the frontier of the country, and so there was not a lot of
really
settlement there.
Yeah,
there was nothing really there. It was still being opened up to settlement at that time. So it was in that particular point in time. If it had been just a little bit later, then there would have been a lot of infrastructure and things to knock down, or if it had been a little bit earlier, we may have not even known about it, but it happened. And so there's been an enormous amount of research focused on, understanding, because it didn't come as just one event, it came as a series of earthquakes, and why is that? And what would be the effects of something if it were to happen today? And so we would definitely feel it here in Lexington. You'd feel it down at Vanderbilt.
I guess so, yeah. Why do you know why there hasn't been an earthquake since then? A big earthquake?
Well, I mean, there's a lot of it's not well understood. If you go back and look at the paleoseismic record, in other words, go back and start looking at geologic features, we can understand a little bit more about the timing of earthquakes. So before earthquake instrumentation networks, seismometers, where you could actually record the signals, the vibrations from the earthquakes. Before that, it was a matter of, if you want to know anything about earthquakes prior to that time, then you have to go out and look at geologic record and look at faults and how much they're displaced and what the, and then date the rocks or the sediment that's associated with those broken features to know when they were broken. And then you can establish, you look at enough of these things, and then you can establish how often they occur. And so we, there's, but again, you're looking at things that have uncertainty in it. So there's a school of thought that says that those kinds of earthquakes occur every 500 years.
Right.
And then there's been some other studies looking at how the geomorphology or the drainage of the river pattern changes, and some of those suggest it's more like 1,000 years. So it's only been a couple of hundred years. So it's not, I guess, particularly surprising that we've not had anything large like that since. But if you think about California, once a decade or so they have a fairly large event. But that's in California, the earthquakes there are happening because there's plates interacting. Here in Kentucky, it's right in the middle, and so it's sort of a weak spot in the middle of a plate, and so the stresses that are coming across the crust are interacting with these weaknesses and making these things. So it's a little bit different mechanism.
Yeah.
So it's and most of the earthquakes, of course, occur on the plate boundaries. And so when you get inside, then the mechanics of how this happened, or the mechanics of how the earthquakes happen, it changes a little
More
bit.
unpredictable, maybe.
Yeah, it's a little it's a little bit more unpredictable.
Yeah, wow, that's fascinating. And you did some work in China, in Tibet?
Yes. So we also have a research footprint in China. Again, working with some colleagues at the Kentucky Geological Survey, because here, other than the 1811, 1812 events, we don't have any large earthquakes to study. So in order to learn about how large earthquakes can affect places like this, then we have to go travel to areas that experience and have good records of large earthquakes. So in China, we were working on the Tibetan Plateau. Of course, this is where a lot of
is that a fault?
There's and that's so the Indian plate. India is being rammed into the Eurasian or the south of China, and so this is where
the Himalayas?
Yes, and the mountains come up, and so there's a lot of faults and earthquakes in this area. So we've established relationships with colleagues in China, and we've been going there since. It really started in 2004 at a conference, and then we've met some Chinese seismologists that had similar interests as ours, and so we began traveling over there. We established a cooperative agreement. The Geological Survey and the department and the various groups in China, and so we've been going over looking at almost on an annual basis. I've not been in a couple of years now, but some of the more administrative things that I'm doing now have sort of attenuated my ability to travel quite as much.
How do you feel about these new administrative jobs that you've had to take on?
Oh, well, they're necessary things. I've not trained as an administrator, so and so a lot of it is an unknown, and so I'm learning a lot as I as I go, and trying not to make too many mistakes. The college has been very supportive, and the department, the faculty, and the students, they've been very supportive in helping helping me find my new normal. And so it's all an adventure, and we'll see what happens. I don't anticipate being an administrator forever, but this is how the system works. Everybody takes a turn, steps up, and does this, and then if you spend your time, hopefully you leave it in a little bit better place than you found it. And then go back to doing what you...
Go back to earthquakes.
Go back to earthquakes and doing field experiments.
Oh, yeah. It's fun. How did you sort of get interested in geology to start with?
Oh, and that's a question that's difficult probably for a lot of people to answer. As a kid, I enjoyed being outside and camping and hiking, and I would find fossils or interesting rocks that is like, why is this the way that it is, and there's so many variations in all of this, and why are they not all the same, or what makes them different, and why do some look like they have dead animals or dead plants and things, and others don't. And so that was just a curiosity. And then when I started my university studies, I didn't know what I wasn't really for sure what I wanted to do, so I did what a lot of undergrads do. I started my general education, and I needed a science class, and so I had a physical geology class, and it was like I said, and I was like, oh wow, this is really interesting. It answers a lot of the questions, and talking to some of the faculty, seeing and hearing what they were doing, I said, I think I want to try this. And so that's how, it was not a grand design from the beginning. It was more of, just found my place.
It's pretty nice.
Yeah.
That's cool. Did you go to college here?
I did my undergrad work down at Eastern Kentucky University, and then the civil engineering, and then the MS and PhD here. So I've and then when I so most of the education was local, and then I ventured out professionally, and then was recruited back locally, and then nice. I've it's been one giant adventure since then. That's taken me around the world
and
multiple
going
times.
To California and China, and what are the other states?
All
over America.
Right. We've worked in Texas and all through the Southeast. Of course, on both sides of Tennessee, we've got the New Madrid seismic zone on the west side that covers several states: Arkansas, Tennessee, Kentucky, Missouri, and depending on whose hypothesis you want to think, it could be up into as far as north as Illinois.
So it's kind of debated.
It's still debate. So there's still a lot of things. People have been been working on it really since the early 1970s, and that's when the area really began. There was a lot of research effort began during that time, and so that's been quite a while. We've learned an enormous amount about the interplate seismicity, but there's still a lot more
Yeah.
to learn. And so there's more doctoral dissertations and master's theses to go to solve the problem.
A lot more people's lifetimes
That's right.
dedicated to it.
That's right. Every time I always, if I'm on the Tibetan plateau I always find my way back to New Madrid. There's a lot of curiosity. A lot of it is because in California you can go out and you can see the fault. You can touch it. You see it on the surface.
It's a big crack.
Yeah, you see the fracture right at the surface. And in the New Madrid, for the most part, there's a couple of exceptions, but most of it is the faults are buried beneath.
They're like cracks deep down underground.
Right, and they're covered with all of the Mississippi River fluvial materials and some of the older. At one time, the Gulf of Mexico came all the way to Paducah. Paducah was like essentially the shore of the old.
Oh, really?
Yeah, huh?
What, thousands of years ago?
Yes, back in Cretaceous
right.
times, and so there's a lot of sediment and sands and clays and things that have
probably like shells and things.
Mm-hmm, mm-hmm.
Wow.
And so that's filled in over top of it, and then later on the Mississippi River and all of the sands and things with that. So it's been masked, and so it takes it really requires geophysics to do imaging, and so I'm very interested in geophysical techniques to image faults and what the faults look like and how much movement that there's been on them and those sorts of things.
How does one detect these kind of faults underground? You just have like radar or some super sophisticated machines?
No, it's simple physics. I mean, it really is. It's the physics that we use have been known for centuries. It's just that we've developed the technology to apply it better. So we use it's sort of a scaled down version of what industry uses to look much deeper in the Earth's crust to find oil and the fuels and things that keep us going. But we'll take out cable and seismometers, or essentially little coils with a magnet in it, and so you hit the ground you can vibrate it, you can hit it with a sledgehammer, you can detonate a dynamite, you can do, there's many, as long as you create a disturbance on the ground. And so I do that, and then disturb the ground, and then the seismic waves, or these elastic waves, will propagate down through the material, and when they come to a boundary where there's so the energy goes down as a wave, and when it hits a boundary that has that marks a difference between elastic properties, then part of the energy will continue down and part of it will be reflected back. And so we take these reflections and manipulate them in not overly sophisticated ways, and we can produce seismic energy. Step out here. Let me just as a demonstration, I'll show you what. Hey, fine. And so here's some geophones, and so we've got just a hammer. We hit a plate, and so here we can see, just with a tiny hammer, we can see 100 meters at about 300 feet or so down. And so here's a fault. The fault is coming right.
So this is a real map.
That's a real image.
What the ground looks like.
Mm-hmm. That's beneath the ground. So if you were to take a giant backhoe that could reach down 200 meters or 600 feet and get a trench, and you looked at the side of the trench, this is what you would see. You'd see these boundaries in here, and then you would see here that there's a fault.
And you can tell just because it's sort of
Yes.
slanted right there, kind of a
So
crack.
yeah, so it's bent because everything's when water lays
Yeah.
down the sediment, it lays it a very flat, uniform way. And so when you see these bends, and so this is up and this is down. That's
Because
the
they're
other.
crushing against each other.
Right. So this part has dropped, and this part has come up. And
Wow.
so these are the faults. This is, so we can develop these map faults. And if you look close, so this is the cartoon view, but if you look, you can see how it's shattered. The rock is shattered, almost like glass.
Yeah.
And so these things, and so these are at the surface. But once you get to the Ohio River, here's that Mississippi embayment which is really the shoreline of the old Gulf of Mexico. So
Yeah.
you've got all of these sands and gravels that essentially just cover this up. So that just continues on. We just can't see it. And so these earthquakes are being reactivated along these old cracks and broken
Yeah.
this broken rock.
Wow. I clicked on the link on the website where it's like the map of Kentucky and all the sites, and then click on one, and it's a graph of just all these like zigzaggy lines. And I thought that was cool because it looked to me like the ground is just always vibrating, like a little bit,
It is.
which I didn't really realize.
That's right. I
Yeah.
mean, if we were to, and so up on the shelf here, this is an old earthquake. This is an old seismometer that we had down in the ground, and you can see, over time it's been, but
Yeah.
that's and so if we set that in the ground, there's noise all the time. Right now, if that were a working seismometer, I could hook it up, and it would look like this place is falling down because the fan noise, people walking around, the wind blowing against the building, just everything makes imparts energy into the earth, and that energy is manifested in terms of waves. So it's like, not that if you drop a pebble in the water and you see the waves
Yeah.
ripple out from it, that's essentially what we're talking. If I hit, we can't see it, but if we had really high resolution vision and could do that, then we would see ripples moving away from the tapping on the floor. And if we have, and these have the resolution, unlike our eyes. Now our ears can hear it because in addition to putting energy in the concrete here, I've also disturbed the air around it, and so the air is propagating waves, and our ears are essentially seismometers, and so our eardrums vibrate, and then that sends a little electrical signal up through our head, and we it's like, oh, that's that was a car passing by, or that was we can correlate
It's cool.
various sounds, and it's just because the waves, the wave trains are a little bit different, and so we do the same things with the earthquakes. We look at the waveforms, the shapes, and all of that, and then that can tell us something about what the interior of the earth looks like. So it's really a fascinating thing.
And then, if there were to be like a huge earthquake, how early would you know that it was going to happen?
Oh,
Would you be able to predict it all?
So, if you're asking me, I would know when you know, because I'm not. So earthquake prediction. If I could honestly say yes, I can do that.
Can you really do that?
Then I would be promoted. I would be like some kind of Nobel Prize winning scientist at that time. And think about it. We study these we can't see down in the earth, so we have to do it with these remote sensing type devices or instruments, and they happen at discrete points in time. So we have to have our seismometers. We have to be lucky enough to have them where we can best record the signals, and we don't always do that. So we learn a lot, but there's still a lot of unknowns and uncertainty in that. But if you think about, you talk about prediction, just weather prediction. Now, in meteorology, they have satellites and things, and so instead of having one event, we're recording the atmospheric system as a whole, and we're doing that in the continuum. There's no breaks in it, and we've got models, and and these models are because there's no breaks in the input data. We're constantly being able to revise and improve. Yet we still miss. It's supposed to rain today. Well, okay, or it's supposed to be sunny and it rains. So we still miss, and so as good as weather forecasting is, there's still just but it's orders of magnitude more sophisticated and better models than earthquakes. So there's a lot of people working on it, and there's things they're doing like early, because there's there can be foreshocks, there can be things that can happen prior to an earthquake that can give you maybe a few moments, few hours, maybe. And so there's, but as far as saying, on December 8th of this year, we're, you better not be in this town, because it's like if somebody tells you that, hold on to your wallet, because that's just not possible yet.
But one day maybe.
Well, I mean, it's like there's always there's always new discoveries that are game changers. So if I could project myself into the future, decades or maybe centuries, and find that that problem had been solved, I wouldn't be overly surprised. I'd be really curious, but by how it was done. What we do is we try to anticipate. It's like what areas are most likely to have an earthquake, and so in my research, that's a lot of what I where are these faults at? What size earthquakes could this fault generate? And then what would happen if that fault did that in this area? And so we can do a pretty good job of forecasting what the ground motions would be. So if given an earthquake of this size at this location, we can pretty much tell you what would happen to in relative terms compared with just forecasting when it's going to happen in time. We know a lot about what would happen. What we don't really know is when it's going to happen.
Okay.
So there's that, the time dimension is a very, it's a very difficult, it's a very difficult problem to overcome, because as you can well imagine, that the Earth is composed of so many. It's such a complex system, and earthquakes, the complexities of the earthquake mechanics, all the things that go into it. There's so many unknowns. As in math, too many unknowns, not enough equations. So you're kind of like have this indeterminate answer. And so until we start eliminating some of the unknowns, or develop some new theories that will help us expand our fundamental equations, then we're stuck just saying, well, if an earthquake of this size happens here, this is what we can expect. And so we do a pretty good job with that.
Well, I feel pretty safe from
Yeah.
earthquakes in your guys' hands.
Okay, well, good. We live in Lexington. I never want to say there's no way an earthquake. Because we have faults around here. They've just been dormant for a long period of time, but you never know. We're in here in Lexington. We're far enough away from the active seismicity. We don't have a lot to worry about. We would feel it, but we wouldn't expect San Francisco style damage.
Yeah. All right, well, I think that's all I'm going to ask you today.
Okay, well, hopefully I didn't
That was great. No.
filibuster
No, of course not.
at all of your questions.
No, I didn't even really want to ask these questions. Let's see here.